going to cover, this is subgroup section 5, okay? So today, we're going to have part of this section. Okay, the other half will be sent to you as another task. Okay, it's either we're going to do another seminar, or I will just post a video tutorial. Okay, so for today, we're going to look at notation and terminology we're going to use from now on. And after that, we're going to look at definition of subgroups, of course, and then I will leave you with a practice of drawing a subgroup diagram that you will post on your future. Okay, so you're going to look at notation and terminology that we're going to use from now on. Okay, so what we have seen so far, we are familiar with using the symbol of a asterisk here. Okay, but from now on, we want to be more in line with algebra. Okay, we are in algebra environment, so we are going to not to use this symbol. Okay, we use this symbol in the previous section because we want to introduce binary operation. Okay, but from now on, we want to study more concepts, so we try to avoid writing this notation. Okay, so instead we are going to use additive or multiplicative notation. Okay, additive notation is a symbol of addition, and then multiplicative notation we will just use juxtaposition notation. Okay, juxtaposition means that if you want to multiplicative notation for, let's say, for A asterisk B, so we simply write AB, right? So if you want to write an operation of B asterisk A, okay, under juxtaposition ataupun multiplicative notation, we just write BA. Okay, so we or in algebra we either use this notation or juxtaposition notation. Okay, so this is an example. If we want to use the additive notation for the sum of A and B, is written as A plus B. Product of A and B is written as AB. Okay, so please note that sum here is not necessarily means the usual addition. Okay, and also the product here is not necessarily the usual multiplication. Okay, because what we say here, we call this as notation. Okay, as notation only. Okay, of course, if we work in a set of numbers, we know that addition is the usual addition and multiplication is the usual multiplication. That is, if we work in usual set of numbers, integers, real numbers, rational numbers, and so on. But afterwards, we're going to look into some groups that consist of not only integer. For example, in section 8, we're going to look at symmetric group permutation. Okay, that is an example of a group that does not contain integers. Okay? And in that chapter, we're going to use juxtaposition notation. Okay. Okay. Then what we mean here is that when we come to that kind of groups, the symbol juxtaposition or multiplicative notation is no longer means the usual multiplication. Okay. And then one more thing that I need to note to you here is about the additive notation. So we usually use additive notation for binary operations that are commutative. Okay, and then multiplicative notation, also stated in the text, we use multiplicative notation for binary operations that are not necessarily commutative. Okay, so means that it is safer for us to use multiplicative notation instead of additive. Okay, it also means that multiplicative notation can be used for any binary operation, while additive notation can only be used for commutative binary operation. Okay, that's why I said multiplicative notation is safer. It means that it's safer to write our operation as this, juxtaposition. Okay? Okay, those are notation for operation, for the binary operation. Next is the notation or symbols for identity. Okay, so we use symbol 0 to denote additive identity. And we use symbol 1 to denote multiplicative identity. Okay, so again, 0 does not necessarily mean the integer 0, and 1 does not necessarily mean the integer 1. Okay, because again, if we work in a group of integer or numbers, we know that 0 is 0, but somehow in the more general case, these are just a notation. Okay, so additive identity means that identity for groups where the binary operation follows additive notation here. Means that you can have an informal understanding that we're talking about additive identity for operation that are commutative, and we use 1 to denote identity for operation that might not be commutative. Okay, so we can use this notation 0 and 1. Okay, and then this is the operation, the identity, and then next is for inverse, notation for inverse. Before that, we use A prime for the inverse of element A in a group. Okay, again, if an element is from a group, it must have an inverse, a unique inverse. Okay, so now we're going to use notation A to the power of -1 in multiplicative notation. Okay, means that it is more general to write our inverse in this notation. Okay, but sometimes you can also see an inverse notation that is in this form, minus of A, also an inverse of A, but in additive notation. Again, it means that we're talking about inverse of A, particularly came from a group that the operation is commutative. Okay, I mean that this is a symbol that can only be used when your group is abelian, and then this is a symbol that we can use for any group. Okay, so I hope all of you are clear about this notation and terminology that we're going to use forward. Okay, there's also another terminology that I need you to read on your own. I need you to read your text, the terminology of factors versus summands. Okay, these two are has a similarity, and of course they are different. Okay, so I need you to look at that in page 50 of your text. Okay. Okay, now we before we define subgroup, we define order of a group. Okay, so we consider a G as a group. Okay, notation for a group. Consider you have group G. The order of group G, or denoted by this something like modulus sign. Okay. Okay, something like modulus ni. So this is the order of G. Order of G is the number of elements in G. Okay, so we recall that from section 0, we have that for any set S, the modulus of S, symbol modulus, we use for cardinality. Also number of elements in a set. Okay, but that we use term cardinality for set, and for group, we use order. So whenever you hear order in your readings of group studies, so you need to always relate it to the number of elements in that group. Okay. So for example, if we have our usual example from the past, we have integer modulo 4. So integer modulo 4 is a group under addition modulo 4. So we know that that group, because it is a finite group, we can easily find its order. So the order for integer modulo 4 would be 4. Okay, so we have 4 elements in there: 0, 1, 2, and 3. Okay, so now we define our subgroup. Okay, subgroup. Formally, we define our subgroup. So we say that we consider a subset of a group G. So you have a group of G, take a subset of the group G. Okay. So if the subset of group G is closed under the binary operation of G, okay, so means that I take a subset and then I operate each of the element in there under the binary operation of G, and it is still closed. Okay, so I can bring it to this study of subgroup. Okay, so what will make it subgroup is that not only the binary operation from G is closed in H, we also need to see that, or to check that if H with the induced operation from G, the operation tadi, is itself a group, then H is a subgroup of G. Okay, so means that informally speaking, we need to see in H, H is a group or not. Okay, so means that you have to relate back to the group definition. Means that, well, first we know that H is closed under the binary operation of G. Next, we need to check for H whether it is a group. So means that you need to see whether if you look at definition of group, you might want to check for whether the operation is associative. But because the operation now is induced from G, we know that of course the operation is associative because it is the same operation. Okay, so it means that we can skip for the check of axiom 1. So next is you need to check whether the identity is in H. It means that the identity in G is also in H. Okay, and then finally, for each element in H, you must also have the inverse in H again. Then H is a group. When H is a group, we say that H is subgroup of the group G. Okay, so we use this notation. Okay, notation H subgroup G. Okay, we use this less or equal notation here to denote subgroup. You can also use notation of less than with no equal to denote that H is a subgroup of G, but H is not equal to G. Okay, because if H is equal to G, it still can be a subgroup of G. Okay, because of this definition again. So if I were to write an example, I can write that group of integer under the usual addition is a subgroup of real number under addition. Okay, we have seen before, real number addition is a group. Integer under addition is also a group. Okay, now because addition here is induced from here, because they are the same operation, and integer is a proper subgroup, is a proper subset for real number. Okay, it's a subset for real number. Therefore, we say that it is a subgroup, and then I can omit the equal sign here because integer set is not equal to real number set. It means that there exists element in real number which is not in integer. Okay. Likewise, I can use this notation. Okay, I can use either this notation because it is a proper subset. And then, of course, I can use this less or equal notation as well. Okay, less or equal notation is more general to any subgroup. This one, the third one here, you can see that real number under addition is a group G, but positive rational number under multiplication is not a subgroup. Okay, we can see here that positive rational number, yes, it is a subset for real number, but the operation is not induced from this group. In other words, the operation is not the same with the group G. So it cannot be a subgroup when the operation is not the same. Okay, so we know we can also know that from this definition as well, every group G must also have subgroup of G itself. Okay, because again, G is a subset of G. Okay, from our knowledge of subset. Okay, that's one. And then also we can have a subgroup containing only one element, E, where E is the identity from G. Okay, again, because if we take a subset containing E only, it is still a subset of G, and then of course the identity is here, and inverse for identity is identity itself. So it becomes a subgroup. Okay, so example here, we see that integer is a subgroup of integer under addition. Okay, as well as subgroup containing 0 under addition is a subgroup for real number under addition. Okay, the operation is the same. Subset containing 0 is a subset. Set containing 0 is a subset for real number. And in fact, 0 is the additive identity ataupun identity for addition. Okay, so we can, so whenever we are finding subgroups of a group G, we can always at least find these two basic subgroups. Okay, the group itself and the subgroup containing identity element. Okay. Any questions so far? Okay, if you have no question, we continue to the next definition 5. Okay, because of those reasons just now, we want to categorize our subgroup a little bit further. Okay, so we consider a group G again. Then the subgroup consisting of G itself is what we call as improper subgroup of G. Yeah, the first one just now. Okay, those kind of group, we call it as improper subgroup. All other subgroups other than G itself is what we call as proper subgroups. Okay. Furthermore, the subgroup of containing identity element only just now is what we call as trivial subgroup of G, and then the rest are non-trivial. Okay, looking into the example again, so we recall again example of integer modulo 4 under addition modulo 4. This is a group. We've seen this many times before this. So we note that integer modulo 4 contains 0, 1, 2, and 3. Okay, 0, 1, 2, and 3. So we know that from this definition, integer modulo 4 itself is a subgroup. And then we can now categorize it as improper and non-trivial subgroup. Okay, improper because it is under this definition, and then non-trivial because it is not the trivial subgroup. Okay, of course it contains 4 elements here. So we say that this subgroup is improper and non-trivial. Okay, next we have another basic subgroup that I mentioned, that we call it just now as subgroup containing the identity. So identity for integer modulo 4, we know it already to be 0. Okay, so 0 is a subgroup. A subgroup containing 0 is a subgroup, and then we know that it is a trivial subgroup, and then also we know that it is a proper subgroup. Okay, because it says here other than G is a proper subgroup. So we can categorize subgroup containing identity only here is a proper and non-trivial subgroup of integer modulo 4. Okay, so let's find another subgroup of integer modulo 4. Okay, so let's say I want to find this one. This is also a subgroup of integer modulo 4. Okay, why? Because one, this is a subset of integer modulo 4. Okay, one condition. Second, you check whether the operation is closed in this subset. So we see that to check for closure, of course, we will need to check for every possible ordered pair and then map into this function of addition modulo 4. So we see that 0 plus 0 is 0, is in here, close. 0 plus 2 is 2, close. 2 plus 0 is 2, close. 2 plus 2 is 0. Okay, 2 plus 2 under addition modulo 4 is 0. So close. So we have considered all the possible ordered pair. So of course, this is the operation is close. Okay, then next, you need not to check for associativity because addition modulo 4 came from integer modulo 4. We know that it is a group, so of course it is associative. And then you need to check for identity element whether it's in here. Clearly, identity element of integer modulo 4 is 0, and it is also here in this subset. And then finally, we need to check for inverse for every element in this subset. So inverse for 0 is 0 because 0 plus 0 is 0. And then inverse for 2 is 2 because 2 plus 2 is 0 in this group. So we have shown that it is a group. Therefore, we say that this subset is actually a subgroup of integer modulo 4. Okay, so look at this definition again. It is not a trivial subgroup, and then it is a proper subgroup. So we can further categorize this as a proper and non-trivial subgroup for integer modulo 4. Okay, so that's subgroup. Okay, that's about subgroup. Okay, so then I want to leave you with a practice. Okay, with a practice. I need you. I will post a practice on drawing a subgroup diagram. Okay, subgroup diagram example can be seen on page 52. Okay, prior to that, please read all the examples from 5.6 until 5.13. Okay. So I want you to practice draw your subgroup diagram. Okay, a subgroup diagram of the group that we have seen in practice 3. Okay. So practice 3, we recall that we consider a group of M. M contains the integer 1, 2, 3, 4, 5, 6 under the operation of multiplication modulo 7. Okay, I believe all of you have done this practice, okay, last week. So this is a group, okay, this is a group under multiplication modulo 7. So for of course, for most of us who has already finished this activity, we know that the identity for this group, multiplication modulo 7 is associative, yes. Okay, and then you also need to check for the closure, okay, with closure. So we've seen that it is a close operation. After you draw the table, you can see that the element of every element in the table are also the elements that came from this group, right? For example, if I have 6 multiply 5, 6 multiply 5 modulo 7 is 2, right? 6 multiply 5 modulo 2. 6 multiply 5 is in integer is 30, but under modulo 7, instead you multiply, you minus 28. Ataupun you not minus 28. It's actually 30 divided by 7 has remainder 2. So 2 is the result. So, and then of course you can check for the rest, and then you have drawn. Many of you has submitted the correct table. For example, if you have 5 multiply 4 is 20. So 20 divided by 7 is 20 divided by 7 has a remainder of 6, right? And so on and so forth. Okay, and furthermore, you can check also, I'll also ask you about the inverse, okay, inverse for each of the element. The identity, of course, you know that 1 is the identity because 2 multiply 1, 2, 1 multiply 1 equal to 2, 3 multiply 1 equal to 3, 1 multiply 3 equal to 3, and so on. Okay, and then inverse for each element, you know that inverse for 1 is 1, inverse for 2 is 4, isn't it? Inverse for 2 is 4 because 2 multiply 4 is equal to 1. Okay, and then inverse for 3 is 5, right? Because 3 multiply 5, when you divide by 7, you have remainder 1. Inverse for 4 is 2, inverse for 5 is 3, inverse for 6 is 6 itself. Okay, the 6 multiplies 6, when you divide by 7, you get a remainder of 1, the identity. So we know that we know the behavior of the elements in M. So now you previously you have drawn the table, you have listed out the inverse for each of the element, you have known what is the identity element. So next let us draw the subgroup diagram. So in order for us to be able to draw a subgroup diagram as on page 52, you need to know all the subgroups that are there, that exist under M. Okay, all possible subgroup that can be there. Okay, you cannot miss even one of the subgroup. So usually we will call out, okay, we will list out our subgroups, okay, first before we draw them. Okay, so of course we know that we have the improper non-trivial subgroup M itself. Okay, to be one of the subgroup, right? This is also a subgroup yang basically, and then also subgroup containing one only, the identity. So this will become the trivial proper subgroup. Okay, so at least we have these two subgroups. Okay. So next, we want to find another subgroups that are there. Okay, like just now when we work with integer modulo 4, we have a subgroup of, other than integer modulo 4 and trivial subgroup, we have subgroup containing 0 and 2. So now let's say we want to find a subgroup that contains 2, okay, under this group, right? So what you need to do is, of course, you need to list down what are the elements. Okay, what are the elements? What is a finite group? So we must have 2 itself, because we want to contain 2. So it must contain 2. You know that 2 must be there. And then, of course, for this, for a subset, whatever subset you're going to draw here, it needs to also become a group. Okay, so it means that it has to satisfy closure property, has inverse for each of the element, identity instead. Okay, associativity need not to check. Why? Because M is already a group, and multiplication modulo 7 is of course associative. Okay, so continue to that one. First, I said just now we need to check for closure. Of course, it needs to be closed under the multiplication modulo 7. So if we have 2 in here, we must also have 2 multiply 2. Right? So 2 multiply 2 modulo 7 is equal to 4. Right? So 4 must be there as well. Okay, so 4 must be there as well. And then 4 multiply 2 also must be there as well. So 4 multiply 2 is equal to 1, the identity. Okay, and then you need to check further. 4 multiply 4, you know that it is 4 multiply 4. Now, 4 multiply 4 is equal to 2. It's already there. Okay, and then check for another possible ordered pair. You can see that any other possible ordered pair will again map to this one of these 3 elements only. So we know that this is the subgroup containing 2, or I can call it as the smallest subgroup that contains 2, which you will see again in the next chapter. But this is a naive way of how we find a subgroup that contains 2. Okay, so you can see that the operation is closed, okay, by what we have done just now. And then also we can see that identity is also here, 1. And then we also need to check for inverse for everyone. Is it there? Are they there? So inverse for 2 is 4, okay. Inverse for 4 is 2, because 4 multiplied 2 is 1, okay. And then inverse for 1 is 1, okay. So this subset satisfy all the group requirement ataupun group axiom. Okay, therefore that's why we say that this is a subgroup for M. Okay, because this is a subset of M and this is itself a group. Okay, so I want you to continue. Okay, continue finding the rest of the subgroup. Okay, for example, if you want to find the subgroup that contains 3, for example, then similarly, using this method just now, we can obtain a subgroup that contains 3, of course. And then if you want to start with the inverse of 3, we know that if 3 is there, you need to have 5 as well, because 5 is the inverse for 3. Okay, it depends on how we want to start, whether you want to check for the inverse first. Usually, I would check with the closure like I did in the first step just now. Okay. Closure means that I need to multiply 3 with 3 first. Okay, I need to multiply 3 with 3 first. So that 3 multiplied 3 is 9. 9 modulo 7 is 2. So 2 need to be there. Yeah, so 2 needs to be there. And then 5. I need to have 5 multiplied 5, which is 25. 25 modulo 7 is 4. So 4 needs to be there. 1 also needs to be there because 1 is the identity, right? And then it needs to have a closure property. For example, 2 multiplied 4 must also be there. 4 multiplied 5 must also be there. So if I check for 5 multiplied 4, 5 multiplied 4 is 20. Modulo 7 is what? Modulo 7 is 2, isn't it? Is 2. Sorry, 520, modulo 7 is 6. So 6 needs to be there as well. Okay, 6 needs to be there. And then I can see that from here, when I come to this stage, I can see that the subgroup contain 3 has exhausted all the elements in the group M. So if I work further, I will only find out that this is actually the same with group M. If subgroup contain 3, the smaller subgroup that contain 3 must also equal to the group M. Okay, so this is the subgroup that contain 3. So I want you to continue with the groups, with the rest of the subgroups. Okay, with the rest of the subgroups, and as a practice, we will draw the subgroup diagram on your future. Okay. Okay, so we conclude today's lesson by Theorem 14, of course, okay, with Theorem 14. So just now, we have said it informally. How do we show that, for example, this is a subgroup for this? Okay, so you refer to Theorem 14. I missed it here. I will put it back up in here before I post it on your future. So you can see from Theorem 14, there is a theorem on how to show that H is a subgroup. Okay, like we did just now, we need to check for the closure property, part 1, and then we need to check that the identity is in there, the part 2 of theorem, and part 3, for each element in here, the inverse is also in here. Okay, that's the part 3 of Theorem 14. So that's all for today. We will continue with the practice for this subgroup diagram. Okay, so you use any tools that is needed in order for you to include a picture into your answers box. Okay, into your answers box. There is a menu on top of the form where you can include a figure. Okay, so you draw that figure. It's not a big figure. It's just a simple figure. You will need about 4 notes. Okay. Okay. So that's all for today. If you have any questions.
Sure. Boleh tak ulang balik yang pasal improper tu?
The improper. Why is it improper? Isn't it? Is it?
Yes.
Okay, so integer modulo 4 is improper because integer modulo 4 is the group itself. It's G. This is G. This is the group G. Okay, it is non-trivial because trivial subgroup only subgroup that contain identity only. Okay, so integer modulo 4, of course, is a subgroup that contains all these 4 elements. Therefore, it is not a trivial subgroup lah. We call it as non-trivial. Okay, so we say that this is an improper because of this one, because the first part of the definition, and also non-trivial based on the second part of this definition. Okay. On the other hand, if we look into the trivial subgroup are subgroup containing identity only. Okay, so for this example, the identity is 0. So I take the subset that contains 0 only, the identity. It will become a subgroup, sorry. Okay, subgroup because this is a subset, and this is also a subgroup because identity is here, and inverse for 0 is also in here. Okay, so why we call it as proper subgroup? Because it is not integer modulo 4. Okay, dia kata yang lain, the other subgroups are proper subgroup. okay, other than G. So other than integer modulo 4 must be proper subgroup. Okay, not only this is a proper subgroup, it is also a trivial subgroup based on the second part of the definition. Therefore, I can call this as proper and trivial. Okay, and then on the third one, this is a subgroup. Okay, we have shown that this is a subgroup because of, again, identity is here, inverse for each of the element is in here, and the operation is induced from here, and then this is a subset for integer modulo 4. But because this subset is not equal to integer modulo 4, okay, because this contains 2 elements only, integer modulo 4 contains all these 4 elements. Therefore, I can say that it is a proper subgroup based on the first part, and also it is not trivial because it is not this subgroup. Okay, trivial subgroup, we have this one only. Okay, so I can say that it is a proper and non-trivial subgroup of integer modulo 4 group. Okay, did I answer your question?
Dia 02 tu mana dapat maknanya dari mana?
Okay, 0 and 2 ni is already known, but actually you can find it again using the step that we did here just now.
Oh, okay, faham.
Okay, means that I considered I want to find a subgroup that contains 2. Okay, I want to consider the subgroup contains 2, so I need to have 2 in there, and then I need to have 2 plus 2 in there as well. So 2 plus 2 is 0, right? And so on and so forth. So finally, I get only these 2 elements.
Okay,
if you move, if you move into one more step, let's say you want to find subgroup containing 3, again the same thing. Okay, and so on. Okay, any other question?
So, maksudnya kalau soalan draw tu kena buat table ke?
Draw a subgroup diagram, bukan subgroup diagram macam page 52.
Oh, okay.
Okay, dalam page 52 ada contoh subgroup diagram. I nak you buat dulu, dan nanti bila dah habis this a subgroup diagram for integer modulo 4 particularly is exactly as figure 512. Okay, 512 on page 52. You can see it from there. So we can see that that is the only 3 nodes of integer modulo 4 subgroup diagram, because you cannot find another subgroup other than 0, 2 here. It means that if I want to find a subgroup that contains 1, and then when I go into the steps that we look in group M just now, you will figure out that subgroup containing 1 will equal to this group again. Okay, you do that step by step. And then as well as if you want to find a subgroup that contains 3, if you start with 3, so you need to have 3 in there, and then you need to have 3 plus 3 in there as well. So 3 plus 3 is 2, so 2 will be there in as well. And then 3 plus 2 is 1, so 1 will need to be there as well. And then the inverse for each of them is there as well, and then the identity 0 must be there in as well. So finally, it will equal to integer modulo 4 again. So that's why figure 12, 512 on page 52 looks like that. You only have 3 subgroups for integer modulo 4. Okay, to draw the subgroup, of course, you draw a line from integer modulo 4 to subgroup contain 0 and 2 first. Okay, because 0 and 2 is a subset of integer modulo 4, and then trivial subgroup must be put at the most bottom part of your figure, because subset containing 0 is of course a subset for any subset that you can find, or any subgroup that you can find in the subgroup of integer modulo 4. Ya, tadi ada I have the figure tadi sebenarnya, tapi dia tak keluar kat sini. So sebab tu dia tak boleh tunjukkan sini. So next time nanti I cuba masukkan dalam ni lah. Tapi I nak you finish out first, and then the answer for this subgroup diagram I will put it on this slide. I will put this on the slide, and then only I will share the slide later. Okay.
So, untuk yang praktis 3 tu kan. So, maknanya proper subset dia one lah. Element of one lah.
Proper subset. Proper subset tu bukan maksudnya trivial subgroup ke?
Trivial subset.
Trivial subgroup lah. Yang kita jumpa mula-mula ni. Ini trivial subgroup. Ini yang improper subgroup ni. Okay, misalnya atas sekali mesti ada M, kan? Dan bawah sekali mesti ada this subgroup in the diagram. So kat tengah-tengah tu macam ni nak lukis. Faham tak?
Okay, faham.
Okay. Ada soalan lain? Yep.
Saya ada soalan untuk yang example untuk group integer 4 tu under kalau nak buat 1, jawapan dia dalam nanti subgroup dia akan ada satu je lah.
Tak, ini untuk integer modulo 4 under addition modulo 4 kan?
1, 2.
1 kena ada 2. Ke?
Lepas tu 2 tambah 2. 0.
0. Lagi?
0,
2 plus 1 pun kena ada juga. Betul tak? Sebab dia kena close. Sorry?
2 plus 1, 3.
3 pun kena ada kan? Betul.
0, 1, 2, 3.
Kan? So dia akan sama balik dengan integer modulo 4. So tak perlulah. Dia akan sama macam yang improper subgroup tadi.
Oh.
That's why dia tak lukis kat situ. Sebab dia sama dengan integer modulo 4.
Lepas tu dia punya bawah sekali mesti trivial lah.
Yelah, sebab trivial tu is also a subgroup, dan trivial subgroup of course dia subset untuk subgroup kat atas tu tadi.
Okay. Faham. Thank you, sir.
Okay, you're welcome.
Ini sambungan daripada soalan kawan saya tadi tu. Kalau nak buat subgroup diagram, saya kena pilih yang takkan sama jadi
kalau yang saya jumpa yang sama, you boleh je, kalau tak tulis pun tak apa, nak tulis equal tu dekat sebelah tu pun boleh. Tapi biasanya dia tak tulis lah.
Soalnya akan pilih subgroup yang takkan dapat sama macam
yang tak sama sajalah. Yang dah sama tu kita tahulah dia must be there somewhere in the diagram. Okay, maknanya kita akan keluarkan subgroup yang extinguish lah, maknanya yang berbeza.
Okay. Faham?
Okay.
Terima kasih.
Okay, I will end this call now. Okay, Assalamualaikum.